Le Chatelier's principle on concentration. I bet you've been wondering what it is. Well, we're going to check that out in this video. It's a very quick video because we've looked at Le Chatelier's principle before, and this is the first factor that actually affects an equilibrium system. So that is, specifically, if we add a reactant or a product, and of course we can remove them as well. So adding or removing a product or a reactant will affect its concentration and therefore the equilibrium position. So let's check this out. Remember that Le Chatelier's principle is a principle that basically states that when a system is at equilibrium and there is a disturbance on that system, the system will move in a direction to minimize the change. And in this case, we're going to be talking about concentration effects. So let's check out this example. Dinitrogen tetroxide on the left-hand side, you can see that it's a gaseous reactant, and that forms nitrogen dioxide, which is a brown poisonous gas. But the cool thing is that dinitrogen tetroxide, it's late, is colorless. And so depending upon what we have in a test tube or in a sealed container, it'll either be colorless or be brown, and that allows us to determine which way the equilibrium position is moving towards. So let's have a look at here. Here you can see here a vial of dinitrogen tetroxide, and it's in some dry ice. It's being kept cool so that it can be kept on that left-hand side because it's affected by temperature, which we'll look at in another video. But when it's cool, the left-hand side is favored. Then on the right-hand side, you can see now that when we have some nitrogen dioxide, it's brown. So it's pretty cool gas. It's poisonous, and hence those vials are sealed. So what happens if we add a product? Well, the product in this case is nitrogen dioxide. If we increase the concentration of nitrogen dioxide, the reaction, according to Le Chatelier, wants to move in a direction to minimize the change. So since we increase nitrogen dioxide, it wants to move towards the left to minimize that increase in concentration, right? So it's going the opposite way to what the disturbance was. We disturb it by adding more nitrogen dioxide. The system will move towards the left to minimize the change. Now, of course, there are going to be new concentration values now, right? So let's check out what this picture says. It just says exactly what I said, but in a pictorial format, right? So if we add more nitrogen dioxide, more of it on the right-hand side is going to increase because the equilibrium has been disturbed, and therefore it's going to move towards the left to minimize that change. Now, how can we show that graphically? Well, I'm glad you asked because I'm about to show you. So let's look on the left-hand side there. The original equilibrium is the blue line is nitrogen dioxide, and the red line is the product, is the dinitrogen tetroxide. So the red is the reactant, which you can see on the right-hand side of the screen. Now, if we add a chemical, you're going to notice a sharp peak, right? And I should use the pointer because that's just what we do. So we're going to see that the nitrogen dioxide here, goes up in a sharp peak. That's telling you its concentration in a very small amount of time has changed dramatically. So when you see that on an equilibrium graph, you know it's been added. If it was removed, then the line would go down, right? It would go down. Now, what does that have? Let's describe the change here. Well, you add it, it goes up very sharply. And according to what we said before, if we add more product, it's going to move towards the left. So that means that this concentration on the left is going to go down a little bit, and the concentration of the dinitrogen tetroxide is going to go up. Well, we can see that here it going down, and at the same time the dinitrogen tetroxide goes up. And of course they reach a new equilibrium. All right, so here we have the original equilibrium. We have a disturbance, and the disturbance is by adding some product by that sharp peak, and then it goes down, which is telling you that its concentration now is being reduced a little bit to minimize the disturbance, and then the concentration of the reactant goes up and we get a new equilibrium established. Okay, what about if we add a reactant? Well, same sort of idea. Here's another graph down the bottom here. You can see that we add the reactant, sharp increase in concentration. If we add the reactant, it wants to go in a direction to minimize the change, so that's going towards the right, which means its concentration itself is going to decrease, and we can see that in the graph, right? Its concentration is decreasing, and the product increases a little bit because it's moving towards the right until we reach a new equilibrium. Okay, so they're the, I guess, the equilibrium graphs. You should be able to describe that. You'll get a lot of questions that will say, here's a graph of a system. What happened at time t, or what happened at 2 minutes? And you'll look for the graph and you go, ah, look, that's got a sharp increase, so therefore you've had an increase in concentration. Or, you know, a syringe was added with the gas into the system, caused an increase in concentration, and it spiked, right? And then you've got to describe the change. So that's it for the video. Hope it makes sense for you. Draw the graphs as well as the information, and I'll catch you in the next equilibrium video.